If you would recall, we know that Calc 3 is the easiest calculus because it's multivariable calculus and vector calculus. And so we've already got calculus thinking in place. We know what limits are and how to use limits. We know about the slope of the tangent line. We know about area under the curve. We know our operations of differentiation and integration, and we know what they're for. Find the slope of the line tangent to a curve at a given point. Find the direction that a curve is going in an instant. Find the area under the curve. We know how to do multiplication where one of the factors is continuously variable. We just need to expand on that. So when we first start doing calculus, we limit ourselves. First, we limit ourselves to just functions to make our life easy. This is to make your life easy. That's why we just started with functions. It's the most restrictive way we can connect two variables. We make one variable a function of the other variable. That's restrictive, right? We can't describe it even like a circle doing that, right? A circle would require two functions, plus and minus square roots. So it's a restriction to make require a function, but it's just a relationship between two variables. Then we can expand that to deal with, once we have implicit differentiation, we can expand that to deal with equations in two variables. X squared plus y squared equal r squared. Now we can describe the whole circle with just one equation. Then we want to go even further and we get a little more freedom and we describe equations parametrically. X of t, y of t, make x and y both functions of some independent parameter t. And now we can describe all kinds of stuff. It can double back on itself, do all kinds of crazy stuff. But in all these cases, we are still just describing a one-dimensional curve in two-dimensional space. It's a one-dimensional curve in two-dimensional space. When you're standing on a curve, your only choices are forwards and backwards. No matter how curvy the thing is in two-dimensional space, it's still only one dimension because you're locked on the track and you can go forward and you can go backward. Backwards is just -1 times forward, so that still only counts as one. And it's just going through two-dimensional space. It's two-dimensional space because there's an X, there's a Y. That makes a two-dimensional space. Any questions? So we just need to expand our calculus thinking to cover more things. Functions of more than one variable, equations with more than two variables, and other items. One of the tools that we have at our disposal is our favorite, vectors. And that's what we want to talk about today. So vectors are going to be a useful tool in describing things in higher dimensions. We're going to start with vectors in R2, and then we're going to expand that to R3. So, but vectors, we want to think of this as just a useful tool in describing things in higher dimensions. So vectors are going to be this useful tool for describing stuff in higher dimensions. I use the very technical term, stuff. Let's start at the beginning. I know that a lot of us have seen vectors already because you've been through physics, you do vectors. Some of you have been through linear algebra, you did vectors. Some of you have been through other classes where vectors show up. Like in trig, we talk about vectors a little bit. So, hey, here's some vectors because angles, right? So we're just going to start at the beginning, the way we want to think about vectors. Vectors are quantities with magnitude and direction. A vector is a quantity with magnitude and direction. you don't like me describing vectors as quantities, that's okay. It's supposed to be uncomfortable. That way it sticks. A vector is something with magnitude and direction. This is opposed to, now we have to make a difference with different kinds of numbers. If all we have is a magnitude, that's a scalar. So this is opposed to a scalar, which is just magnitude. A lot of students are scalars because they have no direction yet. Figure out what you're going to do, you become a vector. This is a math class, so we have to have notation for things because heck yeah, we got to have notation for things. When I'm writing vectors, we'll put a little arrow above the name of the vector. They get single letter names. They get single letter names, like all of our variables. But to denote a vector, I'll put an arrow over the top of it. Scalars just the letter. When we're typing, sometimes instead of putting an arrow over the top, because we're typing and we don't have an arrow over the top button, we might use bold for a vector. So this might be bold when typing. But when we're writing, we don't really have a convenient way to boldface things. So we put an arrow over the top. See, now it's bold. When we're writing, we'll use an arrow. And when we're typing, we'll use bold. Usually we unitalicize them too. So it's non-italic with bold. I mean, if you really want to be picky about things. Any questions? This is how we name our vectors. We're naming them just like other variables. They get a single letter for their name. This is probably why I don't have kids, because I would just use a single letter for the name. This is my first kid, A. Second kid, B. My youngest, D. And people are like, oh, what happened to C? Well, despite his name, he was not satisfactory. And they're like, well, what happened to him? Well, why do you want to ask questions that you don't want to know the answer to? I'm just kidding. I do not have any children, any human children. So that's our notation for vectors. When we want to represent a vector, a lot of times we'll just use an arrow. When we can draw vectors with an arrow. And then we write the name of the vector. So we represent a vector with an arrow. The magnitude of the vector is represented with the length, and the direction of the vector is represented with, well, the direction of the vector. So the magnitude of the vector is the length of the vector. The magnitude of the vector is the length of the vector. So if I want to draw a vector with a small magnitude, I'll draw a short arrow. If I want to draw a vector with a large magnitude, I'll draw a long arrow. The notation, because we have notation for everything, this is a math class, we have a notation for everything. The notation for the magnitude of the vector is to put it in norm, which is a double absolute value sign. So our notation for magnitude is a double absolute value sign around the name of the vector. Note that the magnitude is just a length. The magnitude is a scalar. The magnitude of the vector is a scalar. If you just put 1 and make it look like an absolute value sign, I take off 1,000,000,000 points and you get sent all the way back to arithmetic. You'd have to do arithmetic several times over before you got out of that if I took off 1,000,000,000 points. I take off no points for that. Absolute value sign and magnitude are really representing the same thing. For those of you going on in math, it's a norm. It's the norm of the vector. Magnitude is a type of norm, just like absolute value is the norm of a number. But if you want to be cool, 2. Any questions? How's everybody okay? It's great. We're day 2, and it's probably not anything that's very new right now. Some of you might be acting like it's new. It's like, oh, vectors. That way, when you like ace the vector quizzes, you'll be like, oh, wow, I must be really awesome because I just picked this up so fast. Or maybe you're like, oh, I already know this. Sure. I don't know, whatever you need to do to entertain yourself during class, it's all right by me. This is not the only way that we could represent vectors because this takes up a lot of space. If I've got vectors that are wildly different directions, if I've got vectors that are going in 3 dimensions, then all of a sudden I've got a pretty big limitation if I'm trying to draw them on this flat piece of paper, right? Because I don't have a pen that I can like write through space with. So incidentally, those of you who are engineers like, oh, we could build one of those. I don't want that either. Neither do I want to be able to write in space with a pen, because that's just going to make everything way more complicated than it needs to be. Do you know what I mean? I do not, I'm perfectly happy with like flat screens. I don't need everybody sitting in this room with some kind of like Tony Stark hologram where they're like taking notes and like spinning things around and right. I don't need that hologram stuff that Tony Stark was using, where he's like flinging stuff around. On a side note, did Robert Downey Jr. feel ridiculous when there wasn't the graphics and he was just kind of like standing there doing his mime stuff?
He must be pretty fun.
Our mimes everywhere. It's like, and you mock us? Or I think, because they're mimes, right? So a lot of times we'll describe a vector with what looks like coordinates. We'll say the vector starts off at 0, 0, and we'll say the direction from 0, 0 using coordinates. I wrote coordinates. Using components to describe vectors. They're coordinates for points, they're components for vectors. If you think that sounds really pedantic, you're in a math class. Of course it sounds pedantic. It's a math class. Everything is pedantic. So we're going to imagine the tail of the vector to be at 0, 0. We're thinking this is going to be 0, 0. That's the start. And we think about where the end of the vector, where the vector stops. How much horizontal and how much vertical did we do? We did 4 horizontal and 3 vertical. So I would describe this vector with the coordinates 4, 3, but just thinking of that as just like our x change and our y change. It could start anywhere it wants, but how much does the x change? How much does the y change? And there are a few ways that we could describe this vector. I'm going to give this vector a name. This vector is going to be v. And I might say that v is the vector. I might write it vertically and say it's 4, 3. There's describing the vector vertical style, like you might see in linear algebra. We might also want to write it horizontally with the components, but then if we just wrote 4, 3 in parentheses, that would look like a point, and we want to make sure that everybody knows this is a vector, and so we're going to emphasize the pointy parts and put this in pointy brackets. So another way we can describe a vector is with pointy brackets around the components. I don't know what pointy brackets are called. I'm sure they have a better name than pointy brackets, but I'm going to call them pointy brackets. Too close to retirement at this point to change up what I call those things.
I mean, it works, so.
It works, right? Another way we're going to describe these is with our standard basis vectors. So I might say this is 4i plus 3j.
Memory is coming back.
Is that the memories are coming back? Is that bad or good?
I mean, I have physics 250.
Okay.
These last semester.
Yeah, this is how I find out who was in physics. So we got this vertical style. We got the pointy brackets to go horizontal. And then we've got our standard basis vectors. So I and j. Any questions? Just different styles. Don't mix them up. Postmodern jukebox or calculus class. And one problem, like use vertical ones and then square bracket, and then like the brackets and the I and j, all different steps. I don't know. These are just different styles. This vertical style, pointy bracket style, I and j style. Yes. Yes, the I and j are specific vectors. And this one is kind of the advanced version, because this one is actually a linear combination of basis vectors. I is the vector 1, 0, and j is the vector 0, 1. That's bad grammar. I am the vector 1, 0, and j is the vector 0, 1. Now notice I didn't put just a dot over the I and j. I put a little pointy thing. Sometimes this is referred to as I hat and j hat. I can't remember to say I hat. That's too many syllables when I could just say I. And then hope everybody knows that in this context, I'm talking about the first basic, standard basic thing. We might also write this vertically, except I didn't give myself enough space because great planning there, dude. We might also write these as J just with a vector over it instead of a dot. So, and sometimes when you're typing this out, you can actually see the dot above the I and the arrow above that. But I mean, the typesetting due to the printing press is just be like, oh, come on, man. This is just getting excessive. Questions? Comments? Snide remarks? How's everybody? So we can also use components to describe our vectors. Anybody who's never seen vectors before? Incorrect. We just did, and you've seen them before. Ah, trick question. Minus 1,000,000 points. I'm just kidding. It's minus 2,000,000 points. I'm just kidding. It's minus 0 points. That's why we start at the beginning. How's everybody? Okay. See, the strange thing is, while this is sitting for a minute, you gotta let things sit for a minute. And the strange thing is, I don't edit out the dead space in the videos. I just take the raw video and just barf it up onto YouTube. Makes it, no one ever watches. Like, my most popular video on YouTube was from a couple of years ago. I was selling an amp and I wanted to demonstrate that all the parts of the amp worked. And so it was just me like hitting a chord and like making adjustments to show that the switches work and all the knobs work. That's it. Most popular video. That is the part of the show where there would have been a commercial so you could stop thinking about math for a minute. So this IJ notation indicates something that something else about vectors that we need to go over, how we add vectors and how we multiply vectors by scalars. So this has already brought us into operations on vectors. So let's talk about vector operations. Talk about vector operations. Here are the vector operations that we need to know. Vector addition. Scalar multiplication. And then the two kinds of vector multiplication. Vector multiplication comes in two varieties. And I think we talked yesterday about what those two varieties are. What are the two varieties of vector multiplication? There's the dot product or the scalar product. And there is also the cross product, which is a vector product. These are the operations that we can apply to vectors. Vector addition, scalar multiplication, and then two kinds of vector multiplication. The first two, vector addition and scalar multiplication, we combine those two form linear combinations. These are the two that we use to make linear combinations. Specifically for our purposes, these are used in linear combinations of vectors, but vector addition and scalar multiplication, that's what linear combinations are. Whatever our vectors happen to be. I know some of you are familiar with these things, these operations already. Even if you're not familiar with vector addition and scalar multiplication, whatever you guess would happen in these, that's how it works. Whatever you think would happen, that's how it happens. Remember that vector we had earlier? However you think it works, that's how it works. Think back to when you first learned about the derivative. You learned nx to the n minus 1. The derivative with respect to x of x to the n is nx to the n minus 1. And then you had an example where it was like, oh, x to the fifth plus 3x squared. It was like, oh, what up? You determine a time? Yeah. Because the derivative is a linear operator. The derivative respects the linear combinations. The derivative is a linear transformation. It respects linear combinations. So however you guess it would work is probably how it works. That's a great thing that happens in math. Remember the vector that we had before, the vector 4, 3 was 4i plus 3j. It's 4 times the vector 1, 0 plus 3 times the vector 0, 1. If I do 4 times the vector 1, 0, that's scalar multiplication. 4 times the vector 1, 0, would I just multiply everything by 4? Yep. 3 times the vector 0, 1, just multiply everything by 3? Yep. There's your scalar multiplication. Then if I want to add the vector 4, 0 to the vector 0, 3, we had to guess, just add the horizontal ones and then add the vertical ones. Yeah. However we think it will work. That's pretty much how it works. Notice that I even respected the order of operations, and I did the thing that we call multiplication before the thing that we call addition. So we'd say the vector 4, 3 is a linear combination of the vectors 1, 0 and 0, 1. So if I had two other vectors, so if the vector v is 4, 3 and the vector u is -2, 5. So if v is 4, 3 and u is -2, 5. The vector v plus u, I would just add the corresponding components. That's a linear combination of those two vectors. If I wanted to find the vector -2 v, I would just multiply all the components by -2. Which is just how we think it would work. It looks like I distributed the -2, but I personally would not say it that way, because I think of distribution as an interaction between operations, and there's not really an operation. The vector 4, 3 is just the vector 4, 3. Those are the components. There's not an operation. So I'm not thinking of distributing the -2 to the 4 and the 3. Distribution is multiplication distributes over addition. Now I think of the operations interacting. This is because I'm excessively pedantic. This is because I've been teaching math for 20 some odd years, so of course I'm going to be excessively pedantic. I try not to be, but when I'm standing in a classroom, oh, fuck, I can't help it. I don't think anybody here has been in my linear algebra class, but then it's really bad. Like when I'm doing linear algebra, you don't get to use the word it at all. It is inconsistent. I'll be like, oh, what is inconsistent? Any questions? Also in Calc 2, you're not allowed to use the word it. Now, visually, we have these vectors, and we can stack them together. I have the vector v plus u. So the v goes in this very specific direction. I'm going to draw it very carefully. Here's 4, 3. And the vector u goes in the direction -2, 5. And so the vector v plus u will start at the end of v, start at the beginning of v and go to the end of u. We just kind of do those two things at once. And there's the sum of the vectors. Notice that this is called addition. One of the things that we have, when we have something that we want to call addition, it has to be commutative. Addition needs to be commutative. Multiplication, not so much, but the addition, that needs to be commutative. Otherwise, we can't call it addition. If I wrote these in the other order, if I drew u first and then v, we would end up at the same spot. So if I did the vector u first, and then the vector v, we would end up with the same resultant vector. Vector addition is commutative. It had better be, we are calling it addition. U plus v is equal to v plus u. In the second example, I've got -2 times v. I've got a scalar multiplied by a vector. All we're doing is scaling the vector. We're multiplying the magnitude by 2, and the negative is changing the direction. So I'm just going to take 2 copies of v in the opposite direction. And there'll be the vector negative 2v. Any questions? How's everybody okay? Told you Calc 3 was the easy one. It's like vectors. Again. You're going to be as tired of talking about vectors as you are of hearing things that like multiplication or integration is multiplication, but one of the factors is continuously variable. So here we are making linear combinations of vectors by combining them with scalar multiplication and vector addition. We're making linear combinations of vectors. These are the same linear combinations of vectors you talked about when you were in linear algebra. Multiply that by -1, and how you phrase it if you haven't taken linear algebra yet. So there are two kinds of vector multiplication: the inner product, scalar product, the dot product, or the cross product. Our favorite one is going to be the dot product, the scalar product. Here's how we want to think of the dot product. The dot product is when we're multiplying at an angle. The dot product is when we're multiplying and our two quantities are not going in the same direction. Dot product is multiplication at an angle. Dot product is multiplication at an angle. This hasn't been a concern because everything that we've dealt with were functions of one variable. We've been dealing with real numbers. All our quantities have been real numbers up to this point in our mathematical career. And on the real number line, there is just the one direction. The positive direction, -1 times the positive direction. So it still only counts as 1. So if I did 2 times 5, I'm taking all the 2 and multiplying it by all the 5. And I'm getting 10. 10? Yeah, 10. But now that we have vectors, our quantities might be going in different directions. So what if I have 5 going horizontal, but my 2 is at some wonky angle? I'm not going to get all the 2 to get multiplied by the 5. I'm not going to get all of the 2. This is where we're going to find the dot product of things. When direction is an issue, our multiplication is going to be the dot product. It's like we're multiplying the two magnitudes, but they don't agree on what direction they're going. So we're not getting all of them. We're getting some part of it. Multiplying magnitudes that aren't going in the same direction. It works if they are going in the same direction just fine, but it's multiplying magnitudes that aren't going the same direction. That's how we want to think of it. The dot product, the way I phrase that is I say the dot product is multiplication at an angle. 2 times 5 is 10, when the 2 and the 5 are both in the same direction. We need a dot product if they're going in different directions. Any questions? Note I haven't told you how to calculate the dot product. If I tell you right now how the dot product is calculated in this context, then you will instantly understand all of vector calculus. It will just snap into place instantly. It's weird when I do this. Like the second day of calculus, and I just make it all snap into place right away, just by explaining what the dot product is in more detail than just this simple phrase. But I have to do it right now. If I wait until like just even till tomorrow, we have to go through vector calculus at the normal pace. So I'm just going to explain. I'm going to make vector calculus simple for everybody in the room, like right now, just by explaining what the dot product is. Everybody ready to receive like a matrix download all of vector calculus in an instant?
Yeah.
Let's go. Oh, shoot, look at the time. That's gonna do it for today. I will see you all on tomorrow. Everybody have a good day and thanks for playing.
Bye.